Here we will see Green's theorem. So let's consider we have a xy plane and in this xy plane lies a vector field, let's say V. So here lies a vector field V. So pictorially it looks something like this. It can have other form depending on how this vector field V is described in terms of x and y. So this is a xy plane. So in general, this vector field V will have two components, one along x-axis and other along y-axis. So let's suppose the most general form it takes is this one, from I cap and j cap. So this is our vector field, and our question is, what is the circulation of this vector field V along a closed curve? And let's suppose our closed curve is this one. So this is our closed curve. Let's call it C. And our question is what is the circulation of this vector field V along the closed curve C? So that same statement is defined mathematically this way. So what this says, it says calculate the line integral of V along this curve C. So if V is having these two form M and N, so according to Green's theorem, this same expression can be calculated other way also, and that is how? It is this way. So you have to calculate the area integral of this integrand. So this region R corresponds to the region bounded by the closed curve C. So how do you prove LHS with RHS? So let's start. So here dr is nothing but dx I cap dy j cap. So this is expressed in Cartesian coordinate. So you see here V is circulating around the curve. So let's suppose that circulation is along anti-clockwise direction. So this is the anti-clockwise direction. So when you write this expression in Cartesian form, you get something like this: m I cap plus n j cap. So this is the expression of V, and expression of dr is dx I cap dy j cap, and from here you will get m dx plus n dx and dy. So now the question is how to find m dx. M dx is nothing but the line integral of m along this curve. So x goes from here, this point, let's suppose x goes from here to here. So this is point A, this is point B. So x is traveling from this point here up to this point, and then again it is coming back via the upper curve. So let's call the lower curve y1 as a function of x, and the upper one y2 as a function of x. So this part you can calculate this way, and since it is a function of x and y and we are considering the lower curve now, so we have written y1, and this integration will go from a to b, and we have to take the full circulation, so we have to include the other part b to a. So b to a correspond to the upper one, this one. So it goes from b to a, and here y2 as a function of x, y1 as a function of x. So what is this value? Let's calculate. So you see now, if you change the order of integration, the second term will give this. It will give minus sign. Now you can take dx common, a to b, mx y1, mx y2. Dx is common. Now you see here, you can write it this way also. M as a function of x and y goes from y2 to y1. Okay, so these two expressions are equivalent. So this expression and this expression both are equivalent. So when you put this limit, you recover this two term. So let's move ahead, and we will like to write it in this way. y2 means y1 to y2. So we have to change the order, y1 to y2. So when you change the order, there will be a minus sign here. Now again, you see this one you can write a to b. This whole thing can be written this way also: partial derivative of m with respect to y, and then again you integrate with respect to y, right? And integration goes from y1 to y2, and the claim is this whole thing here is equivalent to this whole thing. Have a look, you will see that both are equivalent. Now this one we can write a to b and y1 to y2. This is dx dy. So you see, this is going from a to b, x limit. X is going from a to b and y is going from y1 to y2. So basically our curve was this, and a and b, y1 to y2, right? So it is going from a to b and y is going from y1 to y2. So actually it is tracing this whole region. So this whole thing you can write this region R, dx and dy is nothing but dA. Alright, so now you are integrating over this region. Okay, so this is your infinitesimal area dA. So you are now integrating over this area. What you are integrating? Partial derivative of m with respect to y. So we have just seen what this m dx is. So m dx is minus over the region R partial derivative of m with respect to y dx dy. Similarly, when you calculate this one, you will get same thing, except now here partial derivative is with respect to x, and there is a plus sign here. So when you rearrange this one, you get this term on the right side. So we have just proved the Green's theorem. Hope you have understood. Thanks for watching.